Imagine a user loading into a frame environment.
Okay.
They step into this photorealistic 71 million splat scan of a Tokyo street. And it loads in milliseconds, like on a mobile browser.
Right.
Their avatar casts a dynamic shadow onto the wet pavement as they walk. They, physically collide with a street sign, which actually reacts with proper rigid body physics. And an AI-driven NPC seamlessly navigates around them to cross the road.
Yeah, which sounds like science fiction if we're being honest.
Exactly. I mean, if we were having this conversation 6 months ago, attempting that inside a web browser would have instantly exhausted your VRAM, triggered a catastrophic garbage collection stall, and ultimately just, melted your GPU.
100%. It would have caught fire.
But today, that is the rapidly approaching baseline. So, welcome to the deep dive. We are speaking directly to you today, the Frame development team.
It's great to be here. And we've been watching the commits, the feature branches you've all been pushing regarding Gaussian splat integration. The progress is undeniable.
It really is.
But the computer vision and rendering landscape hasn't just moved the goalposts this summer. It has completely rebuilt the stadium.
Yeah.
So we are synthesizing a massive influx of industry updates, white papers, and platform drops from the summer of 2026.
And the core thesis we are presenting to you, the Frame team, today is basically this. 3D Gaussian splatting has officially graduated.
Yeah.
The era of the baked-in static point cloud novelty where users just sort of orbit a frozen, unlit photogrammetry scan of a shoe is over.
Thankfully.
Right. It is now a dynamic, interactive, fully integrated spatial medium, which means your users are very quickly going to expect your splat environments to be walkable, relightable, and streamable in real time, all within the strict constraints of a web platform.
Which is, a monumental engineering challenge.
Mm-hmm.
Transitioning a volumetric representation of a light field into a functional spatial asset requires solving some notoriously brutal computer science problems.
Oh, absolutely.
But looking at the stack of sources we have today, from web GPU leaps to entirely new rasterization architectures, those problems are being systematically dismantled, like right now.
So let's not waste any time. We have to start with the fundamental bottleneck for Frame, which is the delivery and rendering pipeline.
Right, the plumbing.
Yeah, the plumbing. Because if we want interactive 100 million splat scenes, we have to talk about how we actually get that data into the browser and onto the screen without hitting thermal throttling on a standalone VR headset. Let's look at Play Canvas. They just rolled out some massive updates to SuperSplat, completely migrating to compute-based web GPU rendering.
This is the critical first step for any web-based spatial engine right now.
Yeah.
I mean, WebGL simply does not have the architectural paradigm to handle millions of independent spatial primitives efficiently.
Right.
The overhead of the WebGL state machine, combined with the limitations on uniform buffers and the inability to arbitrarily write to storage buffers from the shader, it just makes it a dead end for dense radiance fields.
Yeah, in WebGL, you're constantly fighting the CPU overhead just to issue the draw calls. Or you're doing these agonizing texture read hacks to pass position and covariance data to the vertex shader. It's miserable.
It's super hacky. Web GPU compute pipelines change the math entirely.
Completely.
With Web GPU, Play Canvas is moving the entire sorting and rendering payload onto the GPU timeline. You map the splat data directly into compute storage buffers. But Play Canvas didn't stop at the API level.
No, they didn't.
They've introduced automatic streamed level of detail, and more importantly, they open-sourced a new format called SOG, which they are actively branding as the WebP of Gaussian splatting.
Which is a bold claim.
Very bold.
But looking at the specs, they are pairing it with the SOGS format for streaming, and they're hitting a 20x compression rate. 20 times.
Yeah, it's wild.
If I'm a Frame developer worrying about payload sizes for mobile users, that is a massive sigh of relief. How are they achieving that level of compression on raw floating point covariance and color data? How is that mathematically possible?
It relies heavily on vector quantization and essentially discarding the higher-order spherical harmonics when they aren't strictly necessary.
Okay, break that down a bit.
Sure. So a standard PLY file from a Gaussian splat capture is incredibly bloated. You have 3D position, 3D scale, rotation quaternions, opacity, and often up to 3 degrees of spherical harmonics for view-dependent color.
Right, so that's a ton of data per splat.
Exactly, and all of that is stored as uncompressed 32-bit floats. It's massive. SOG compresses this by quantizing the scales and rotations and packing the base color into much smaller integer formats.
And when you pair that with the SOGS streaming format, you aren't forcing the browser to download a 2 GB PLY file into memory before the first frame even renders.
Right.
You stream the lowest LOD first, establish the spatial boundaries of the room, and then slowly page in the high-frequency details.
Precisely. And we are seeing this exact architecture mirrored in World Lab's latest release, Spark v2.0. They are pushing what they call the RAD streaming format, which explicitly utilizes a virtual memory paging system paired with a new LOD splat tree.
Okay, hold on. Paging virtual memory inside a browser environment makes me immediately sweat.
I know.
Because Frame operates in a browser. If you start aggressively paging massive chunks of 3D data in and out of the browser's memory heap, you are going to trigger the JavaScript garbage collector.
Yes.
And the user is going to experience a massive frame stutter right as they turn their head. It's unavoidable. So how is Spark v2.0 managing eviction without just completely killing the frame rate?
Well, they avoid the JavaScript garbage collector entirely.
Wait, really? How?
By managing a fixed-size ring buffer directly in WebAssembly and the WebGPU VRAM, they aren't constantly creating and destroying JavaScript objects, which is what triggers the GC stall.
Ah, okay.
They allocate a massive contiguous block of memory upfront, say 500 megabytes, and they treat that block like a virtual page file.
Okay, I'm following.
As the cameras view frustum moves, the web worker streams the RAD chunks over the network and writes them directly into the pre-allocated WebAssembly heap, which is then mapped to the GPU buffer. The old, out-of-view data is simply overwritten.
Wow. So the memory footprint remains entirely static from the browser's perspective. That's brilliant.
Yeah, it's essentially treating the browser like a thin client for a custom memory controller. And they are claiming this handles scenes with over 100 million splats on standard mobile phones.
That's just staggering. But getting the data into VRAM efficiently is only half the battle, right?
Right. The GPU still has to actually sort and rasterize it.
Exactly. And this brings us to what I consider the most important rendering white paper of the year from NVIDIA, HIGS, or hierarchically tiled Gaussian splatting.
Oh, absolutely. This paper addresses the core architectural flaw in how we've been rendering 3DGS since the original Infuria paper dropped.
And frame developers know this pain intimately. When you look at a dense cluster of splats, the frame rate just tanks. Why? Because of how the tiled rasterizer handles warp divergence and thread serialization. Can you break down exactly what HIGS is fixing here?
To understand the fix, we have to look at the original rasterization pipeline. It basically divides the screen into a uniform grid of tiles, typically 16 by 16 pixels.
Right.
The pipeline operates in two main phases. Phase 1 is spatial partitioning. It takes every splat in the view frustum, calculates its 2D screen space bounding box, and duplicates the splat ID for every 16 by 16 tile it touches.
Okay, so a single large splat gets listed in multiple tiles.
Exactly. It then creates a 64-bit key for each instance combining the depth of the splat and the tile ID, and runs a massive radix sort across the entire GPU to guarantee strict front-to-back ordering.
Right, because without perfect front-to-back sorting, the volumetric alpha blending breaks down and you get those nasty popping artifacts.
Yeah, it looks terrible. So phase 2 is the actual rasterization. The compute shader assigns a thread group to each 16 by 16 tile. The threads iterate through the sorted list of splats for that specific tile, accumulating color and alpha until the pixel reaches full opacity, at which point it culls the rest.
Which, sounds highly parallel and efficient in theory, so where does the pipeline choke?
It chokes because both the spatial partitioning and the rasterization are chained to that exact same 16 by 16 tile size. These two processes have fundamentally opposing architectural needs. Sorting millions of duplicated splat IDs across thousands of microscopic tiles is incredibly expensive for memory bandwidth. Partitioning desperately wants larger tiles to reduce the sheer volume of key value pairs being generated and sorted.
It's like having a restaurant where one waiter is forced to take all the orders for a massive 50-person table, while the other waiters just stand around doing nothing.
That's actually a great analogy.
But the rasterizer wants the exact opposite of the partitioner, right?
Precisely. The rasterizer wants small tiles so it can maximize occupancy across the streaming multiprocessors. If you have a massive, highly detailed 50 million splat tree in the center of your screen, the 16 by 16 tiles covering that tree might have 100,000 splats queued up.
Right.
The SMs assigned to those specific tiles are locked in a massive serialized loop, iterating through all 100,000 splats. Meanwhile, the thread groups assigned to the empty sky finish their tense glass instantly and then just sit completely idle.
So your entire GPU utilization plummets because you are bottlenecked by a handful of overloaded thread groups.
Yes, it's the classic load balancing nightmare. You have warp serialization destroying your compute efficiency.
So how does NVIDIA's Higgs architecture decouple this? How do we assign a team of waiters to the big table?
Higgs breaks the lock. It introduces macro tiles for the sorting phase, while preserving the microtiles for the rendering phase.
Okay.
Instead of projecting and sorting splats into 16 by 16 pixel grids, the initial projection and radix sort happen over much larger macro tiles, say 256 by 256 pixels.
Okay, stop right there. If you sort over a massive 256 by 256 macro tile, how do you not lose the pixel-perfect depth sorting required for the alpha compositing at the 16 by 16 level? Doesn't the whole thing break down?
That is the genius of the paper. They maintained exact front-to-back visibility.
Oh.
The sorting at the macro tile level orders the primitives. Then, during the rasterization dispatch, instead of assigning thread blocks based strictly on screen space tiles, Higgs issues the rasterization work proportionally to the density of the primitives in each macro tile.
Oh, wow.
Yeah.
So if a macro tile has that dense 50 million splat tree in it, the scheduler dynamically assigns more parallel thread blocks to chew through that specific macro tile's list.
Exactly. It completely eliminates the thread serialization bottleneck. Dense regions are spread across multiple parallel units. The GPU load is beautifully balanced. The researchers are reporting up to 15.8 times faster rendering compared to the original 3D-GS pipeline, with zero degradation in visual quality.
15.8 times faster? For a frame developer, that is the difference between running a scene at 4 frames per second and locking it at a smooth 60.
Easily.
And the industry is moving aggressively to standardize this level of performance. Look at the WWDC 2026 announcements in our stack.
Yeah, that was huge.
Apple Maps Flyover is getting a Gaussian splatting upgrade, which means Apple is entirely confident in streaming and rendering this data on an iPhone's thermal budget. And visionOS 27 is adding native Gaussian splat rendering directly into RealityKit.
That visionOS update is a massive signal. It means frame developers won't necessarily have to write custom web GPU shaders to draw splats if the user is on an Apple headset.
Right.
It's being handled at the Metal API level by the OS itself.
Right.
Apple is officially validating 3D-GS as a core, hardware-accelerated spatial primitive alongside polygons and voxels.
Okay, so the rendering pipeline is secure,
Hmm.
the splats stream efficiently, they page out of memory cleanly, and the compute shaders are beautifully load balanced. The frame environment renders perfectly. But here is the next wall we hit. You load a user into this beautifully rendered photorealistic room. The user pushes forward on their thumbstick to walk across the floor, and they immediately fall straight through the ground plane into the digital void.
The ethereal nature of the medium.
Exactly. A Gaussian splat is fundamentally just a point cloud of colored ellipsoids. It's like trying to walk on a hologram made of colored smoke. It is an optical illusion. It has zero structural geometry.
Right.
And a gorgeous spatial web platform is utterly useless if you can't walk on the ground, bounce a ball against the wall, or cast a physics raycast to interact with the UI panel. So we need to look at how the industry is solving mass and collision. How do we make the ethereal solid?
This is where we have to bridge the computer vision world with traditional game engine physics.
Yeah.
Physics engines like Havoc or PhysX require rigid bodies, typically represented as boundary volume hierarchies or BVH trees of polygons.
Yeah.
And the most pragmatic breakthrough here comes from Facepunch Studios.
The creators of Gary's Mod. They are the absolute vanguard of user-generated physics sandboxes.
Right. They're building a new platform called SMBox. And during a recent Hack Week, one of their engineers, Carson, shipped an official Gaussian splat library that includes a highly optimized Gaussian splat collider component.
Okay, I have to challenge this immediately. Wrapping a traditional polygonal collision mesh around a raw Gaussian splat sounds computationally horrific.
Oh, it would be.
I mean, the surface of a splat capture is essentially fractal noise. It's millions of fuzzy overlapping shells. If you run a standard convex hull or shrink wrap algorithm over that, you are going to generate a collision mesh with millions of micropolygons. The physics engine will completely choke the CPU on the very first frame. How is Facepunch avoiding that?
By entirely abandoning the idea of polygonal shrink wrapping, they utilize voxelization.
Voxels, okay.
Yeah, they take the 3D bounding box of the splat scene and divide it into a uniform 3D grid of tiny cubes voxels. The algorithm iterates through every single splat in the scene. For every voxel a splat intersects, it accumulates that splat's opacity value.
So it's essentially a 3D density map, like freezing the colored smoke into a solid jungle gym?
Precisely. If a voxel accumulates enough opacity to cross a specific threshold, it is flagged as solid. This generates a watertight, blocky representation of the scene.
But wait, Gaussian captures are inherently dirty. If you capture a living room, you always get those weird, semi-transparent artifacts floating in the middle of the air, reflections, dust, specular highlights the optimizer couldn't resolve.
Yeah, the floaters.
Right. If every splat contributes opacity, won't this voxelization process fill the living room with invisible floating collision blocks that avatars will constantly trip over?
That's exactly why the opacity threshold is just the first pass. FacePunch implemented a rigorous filtering process. First, the cumulative occupancy threshold ignores stray splats. A single floater won't have enough density to trigger a solid voxel. It requires a confident cluster.
Okay, that makes sense.
But more importantly, they run an optional graph traversal pass that isolates the largest connected cluster.
Oh, that is extremely elegant.
Isn't it? It analyzes all the solid voxels and groups them based on adjacency. The primary structure, the floor, the connected walls, the furniture resting on the floor, will inherently form the largest connected graph.
Wow.
All the garbage data floating in the air, even if it managed to pass the opacity threshold, is disconnected from the main graph. The algorithm simply deletes the islands. The floaters vanish from the physics layer.
That perfectly solves the floaters, but what about the opposite problem? Splats only represent the visible surface. They don't have internal volume.
True.
So a floor captured via 3D GS is technically a microscopic thin shell, and it's usually full of tiny submillimeter holes where the optimizer didn't place a splat. If I drop a rigid body physics sphere onto a voxelized thin shell, the physics engine's continuous collision detection is going to freak out. The ball will either jitter wildly or just tunnel straight through the floor.
Which is why the FacePunch library, drawing heavy inspiration from PlayCanvas's splat transform approach, implements distinct fill modes to seal the colliders.
How do you fill holes in a point cloud efficiently?
You don't fill the point cloud. You fill the voxel grid.
Ah, right.
For outdoor environments, they use a floor fill algorithm. It casts a ray downward through every column of the voxel grid. Once it hits the highest solid voxel, the surface of the terrain, it simply flags every single voxel beneath it as solid, all the way down to the bounding box floor.
Oh, I see.
It turns a thin, fragile crust of grass into a massive, impenetrable block of solid earth.
And for interiors, you can't just fill downwards if there's a ceiling.
Exactly. For interiors, they use external fill. It performs a morphological dilation on the solid voxels, artificially thickening the walls to seal any microholes.
Got it.
Then, it flood fills empty space inwards from the outer boundaries of the bounding box. Anything that the flood fill cannot reach, like the interior volume of a room or the inside of a closed drawer, remains empty space. The structure itself becomes an airtight, solid block.
Okay, but let me put my frame optimization hat back on for a second.
Go for it.
Even if this voxel grid is perfectly filtered and filled, managing a dense 3D grid in memory is super expensive. PlayCanvas Supersplat also rolled out their own automatic voxel collision generation, and they are converting splats into 5-centimeter voxels. If I have a 100-meter warehouse scene, a uniform 5-centimeter voxel grid is going to consume gigabytes of RAM just for the collision data. How is that viable in a web browser?
Because they aren't storing it as a dense uniform 3D array, they compress the physics layer using sparse voxel octrees, or SVOs.
Ah, sparse data structures.
Exactly. Empty space costs virtually zero memory. The physics engine only allocates memory for the nodes in the tree where solid geometry actually exists. This means you can have millimeter-accurate collision on the handrail of a staircase, but the empty air in the middle of the room takes up 0 bytes.
That is incredibly efficient. And to be completely clear for the developers listening, this voxelization process does not affect the visual render pass, right?
Yeah.
Do we lose the visual benefits of the splat?
Not at all. The rendering pipeline is still drawing the 100 million beautiful continuous ellipsoids we talked about in the Web GPU section. The user sees a photorealistic scene. The physics engine, running invisibly in the background, is resolving collisions against this sparse voxel octree. Visuals and physics are entirely decoupled.
So you get the visual fidelity of radiance fields with the deterministic, robust collision of a classic rigid body game engine.
Yeah, exactly.
But rigid bodies are just the foundation. If Frame wants to support autonomous agents, AI assistants, virtual pets, NPC avatars navigating these spaces. Rigid body collision isn't enough, and AI needs pathfinding.
Yes, it does.
And that brings us to the LiftNav research paper, TSDF guided Gaussian splatting. What exactly is the limitation of a raw Gaussian splat when it comes to AI navigation?
The limitation is that Gaussian splats have incredibly soft geometry. Because splats are semi-transparent and fade at the edges, calculating a definitive surface boundary for an AI to avoid is mathematically ambiguous. Conversely, traditional robotics use truncated signed distance fields, or TSDFs. A TSDF explicitly calculates the exact distance from any point in space to the nearest solid surface. It is mathematically perfect for safe obstacle avoidance.
But a TSDF is blind. Like it knows there is a solid surface 10 centimeters away, but it has no idea if that surface is a concrete pillar or a delicate silk curtain.
Precisely, it lacks semantics. So the LiftNav architecture fuses them. They use the TSDF for the hard physical zero-crossing boundaries, ensuring the robot doesn't physically crash. But they overlay the Gaussian splat for the rich visual and semantic data. They pass the 2D renders of the splat through a YOLO you only look once object detection network.
Right, the standard real-time object detection model.
Yes, but here's the trick. They take the 2D semantic bounding boxes from YOLO and lift them back into the 3D TSDF splat map. Suddenly, the environment isn't just distance math. The AI understands this specific cluster of solid distance data represents a couch. They then run a B-spline trajectory optimization that factors in both the TSDF distance and the object semantics. The researchers achieved 100% feasibility in collision avoidance.
So for the frame team, if you want LLM-driven avatars walking around a scanned museum, they won't clumsily scrape against the walls or get stuck walking endlessly into a virtual display case. We now have an optimized, mathematically proven pipeline to give them perfect semantic pathfinding inside a radiance field.
Exactly. We have conquered delivery. We have conquered rendering bottlenecks. We have conquered rigid body collision and AI pathfinding. The spatial environment is fast, solid, and navigable.
Which is an incredible milestone. But it leads us to the most frustrating limitation of Gaussian splatting since its inception.
The baked-in curse.
The baked-in curse. Let's say a user loads into a frame environment. It's a gorgeous outdoor scan of a courtyard taken at high noon. The shadows are sharp, the lighting is bright. Now, the frame admin wants to change the environment to midnight and hand the user a virtual flashlight. Traditionally, what happens?
In a traditional 3D GS pipeline, absolutely nothing. The scene remains brilliantly illuminated as if it were high noon, and the flashlight beam passes invisibly over the geometry.
Because every single photon of light is permanently baked into the color data of the splat.
Right. 3D GS optimizes for radiance. It memorizes exactly how light was bouncing off the environment at the exact millisecond the capture was taken. If a bright sunbeam was hitting a brick wall, the splats representing that wall are permanently colored, bright, glowing orange.
It's like taking a Polaroid of a shiny car in the sun. You can't drag a slider in Photoshop to move the sun inside the photograph. The lighting is permanently married to the pixels.
And for a dynamic spatial platform like Frame, that is unacceptable. Users expect dynamic day-night cycles. They expect point lights, spotlights, and dynamic shadows cast by their avatars. But as of this summer, the industry is systematically breaking this curse. We are seeing a massive push towards standardization of real-time relighting.
The offline renderers are leading the charge here. Arnold 7.5.2, Chaos Vantage 3.3.0, Corona 15, these are the heavyweights of cinematic rendering, and they have all natively integrated Gaussian splat relighting. But the most revealing integration is Houdini 22. SideFX integrated 3D GS directly into their Copernicus compositing nodes, but they also built a pipeline to reconstruct splats from Karma CG renders. And the crucial detail here is that they are embedding normals directly into the splat data.
And that is the holy grail for relighting. A normal vector dictates the perpendicular angle of a surface. Without accurate normals, a shader has no mathematical basis to calculate how a virtual light should bounce off a surface or generate a specular highlight.
And historically, we've had to fake this, right? We've had to extract pseudonormals from the depth map of the splats. But depth-derived normals are notoriously noisy. They make flat walls look like bumpy stucco, and dynamic lighting just looks like garbage.
Exactly. But Houdini, proving you can embed and utilize pristine normals inside the splat container, validates the approach for real-time engines, which is why we are now seeing packages like the 3D GS Advanced Shader for Unity. This isn't just color tinting. This is true volumetric relighting that intercepts Unity's scriptable render pipeline. The splats cast and receive dynamic shadows natively.
Okay, injecting normals into synthetic CG splats is one thing, but frame users are scanning the real world with their phones. How do we unbake the lighting from a real-world capture? This is an infamously difficult inverse rendering problem. And this brings us to the most technically fascinating paper on our list, Material Cluster GS.
Yes. Untangling baked lighting from a real-world splat is an incredibly ill-posed math problem. In a traditional PBR physically based rendering pipeline, lighting is calculated using a BRDF, a bidirectional reflectance distribution function.
Right.
This function requires base color, metallic values, and roughness values.
Because rough concrete scatters light widely, so its BRDF looks different than, say, a polished chrome bumper, which reflects light perfectly.
Right. Now, imagine trying to estimate independent BRDF parameters for 50 million individual semi-transparent splats purely from a set of photographs.
It sounds impossible.
It basically is.
Yeah.
The optimizer is given way too much freedom. It gets completely confused. It will look at a dark shadow baked into a white wall, and instead of realizing it's a shadow, it will just assign that specific cluster of splats a dark gray base color.
Ah.
Or, if a splat is slightly out of position geometrically, the optimizer will aggressively alter its roughness value to try and compensate for the visual error.
So the inverse rendering collapses into chaos. You end up with a noisy, unstable mess where the materials are completely wrong.
So how does Material Cluster GS solve an unsolvable equation?
It acts as a massive regularization term. It uses what they call a palette-based material decomposition. Instead of allowing the optimizer to guess 50 million unique materials, it forces the entire scene to share a very compact, global palette of BRDF prototypes. Ah, so instead of letting the math go wild, it restricts it, like an AI separating the physical paint properties from the sun reflecting off it, like a painter's palette. You don't mix a unique atomic color for every single brushstroke on a canvas. You have a blob of matte brick red and a blob of shiny glass blue, and you reuse them.
Precisely. The neural network optimizes a continuous spatial material field alongside the splats. As it trains, it clusters the splats semantically. It learns to recognize that a specific grouping of splats belongs to prototype A, which has the BRDF properties of glossy wood. Another cluster belongs to prototype B, which acts like matte fabric.
So they are extracting the spherical harmonics, the view-dependent baked lighting, and factoring it out, replacing it with a clean base color and a pointer to a specific BRDF prototype on the palette.
Yes. And the implications for the frame development team are extraordinary. First, this massively reduces the memory footprint compared to storing unique BRDF data per splat. But more importantly, it makes the scene instantly editable.
Because the materials are organized. If a frame user wants to renovate their scanned room and they want to make the wooden floor slightly more reflective, they don't have to somehow lasso and edit a million individual splats.
Right.
They just tweak the roughness slider for the wood BRDF prototype on the global palette.
And that single change propagates flawlessly across every single splat assigned to that material in the entire environment. It brings the control of a traditional CAD workflow to the chaos of a point cloud.
I am going to push back on the performance here, though. For a platform like Frame, implementing PBR shaders with BRDF valuations per splat, per pixel, and a fragment shader is heavily compute-bound. If we're running this in WebGPU on a headset like the Quest 3, won't evaluating real-time lighting for 50 million splats completely shatter our frame budget?
It would if you were evaluating a unique BRDF for every splat. But because they are querying a highly compact global palette, the cache locality on the GPU is fantastic.
Oh, that makes sense.
When you combine this palette approach with the Higgs-F macro tile architecture we discussed earlier, which optimally load balances the compute units, real-time physically based relighting on mobile VR hardware is absolutely achievable today. The baked-in curse is broken. You can drop a virtual sun into the skybox, move it, and the scene will cast mathematically correct shadows and specular highlights.
Okay, let's take a breath and look at the stack. We have splats loading instantly over the web via SOGS and .RAD virtual paging. We have the Higgs-F architecture rendering them at 60 frames per second. We have SMBox voxelization, giving the environment solid collision and AI pathfinding. And we have Material Cluster GS unbaking the lighting so we can introduce dynamic day-night cycles.
Yeah.
We have built a fast, solid, perfectly lit 3D environment. What is left for the Frame team?
The final frontier. Moving beyond static architecture and bringing life into the environment. The future of spatial computing is the 4D horizon streaming dynamic, time-varying volumetric data.
Right. And to establish the baseline of where 4D is at right now, we have a note here about the upcoming Superman feature film. The VFX teams are actively using dynamic 4D Gaussian splats to anchor sequences in the film.
which proves that the visual fidelity of 4D splats has crossed the uncanny valley. If it can survive the scrutiny of a cinematic close-up on a 40-foot IMAX screen, it is more than capable of rendering human performances in a spatial web environment.
But cinematic VFX is heavily pre-computed. Rendering farms take weeks to process those frames. Frame is a real-time platform. How do we stream a live, moving 4D volumetric performance into a web browser?
It's all about compression.
Right, because my immediate assumption is that the bandwidth requirements are impossible. If a static 3D splat room is a massive file, isn't a 4D splat essentially 60 massive files a second? That would obliterate standard Wi-Fi.
That is the intuitive assumption, but it completely ignores how temporal compression works. You are not streaming 60 independent meshes a second. Projects like NVIDIA's Play4D research, which is currently being heavily utilized by platforms like Gaussians for the Apple Vision Pro, focus on tracking deformations.
Tracking deformations. So if I capture a person talking and waving their arm, the initial payload loads their static geometry, and then for the subsequent frames, the server only sends the mathematical instructions to move the specific splats that make up their arm.
Exactly. They compress the time-varying Gaussians by calculating the residuals. Most of the scene, the background, the person's torso isn't moving. The algorithm utilizes neural deformation fields to track how the splats shift, stretch, and rotate from frame to frame. It only transmits those delta updates over the network.
It's the spatial equivalent of video compression algorithms like H.264, where it only updates the pixels that change. And this entirely skips the traditional VFX pipeline, right? No retopology, no UV mapping, no complex skeletal rigging and skin weighting. It is purely photographic, volumetric video.
It captures the performance perfectly. But Play4D is primarily for pre-recorded volumetric video. What if we want to stream a live event?
Okay, yeah.
What if we have an array of cameras capturing a physical space, and we want to fuse that into a 4D splat environment in real time inside frame? This is where we hit the occlusion problem and where the refined paper comes in.
Learning efficient fuse and refine for feed-forward 3D GS. Walk us through the occlusion problem. Why does live 3D reconstruction break down when someone walks in front of the camera?
Current feed-forward models try to generate the 3D splats based strictly on the current 2D frame they are receiving from the camera. If a person walks behind a pillar, the camera can no longer see them. Because the algorithm only knows about the current frame, it assumes the person has ceased to exist. It deletes their splats.
And when they step out from behind the pillar, the algorithm suddenly hallucinates them back into existence. You get horrible, chaotic flickering and popping. The 3D model is incredibly unstable.
Precisely. Refine solves this instability by introducing a hybrid splat voxel representation and a sparse voxel transformer.
We are bringing voxels back again. How does a voxel transformer fix temporal flickering?
By giving the system memory, it allows for history-aware online reconstruction. When the system generates the splats for frame 1, it deposits their local features into a sparse 3D voxel grid.
Okay.
Then, when frame 2 arrives, it takes the historical splats from the voxel grid, uses flow algorithms to warp them forward in time based on their trajectory, and merges them with the new splat observations from the current camera feed.
It layers the past onto the present?
Yes, and then it passes this aggregated volume through a sparse voxel transformer. The transformer's multi-head attention mechanism analyzes the entire volume. It intelligently calculates an adaptive fusion weight.
What does that mean in practice?
It learns to say the camera can't see the person's left arm right now because it's occluded, but based on the historical data in the voxel grid, I know the arm is still there. It outputs a single, temporally stable set of refined splats.
It gracefully handles occlusions because it remembers the spatial volume. But again, I have to play the role of the frame optimization engineer here. Running a 3D transformer over a voxel grid, warping historical splats, and fusing hundreds of thousands of primitives sounds like it would take seconds per frame. Real-time requires milliseconds.
Which is why the performance metrics of the refined paper are so staggering. They are executing this entire fuse and refine process on 200,000 primitives in exactly 15 milliseconds.
15 milliseconds, that is well within a 60 frame per second budget.
They're achieving fully interactive rates on a single consumer GPU with a total pipeline latency of only 350 milliseconds. For the frame development team, this is the writing on the wall. The future of your platform isn't just pre-recorded static environments. It is the ability to ingest live, history-aware, dynamic reconstructions of physical spaces into the web browser with zero flickering.
Live 3D streaming of physical reality. But the 4D horizon isn't solely about capturing reality via cameras. It's about generative AI creating reality on the fly. And we have to end our technical deep dive with Spatial. They just shipped a Claude plugin and a hosted MCP server.
MCP, the Model Context Protocol. It is an open standard that allows large language models to securely connect to external tools, databases, and APIs.
Right. LLMs are great at text, but they are isolated. MCP gives them hands. And what Spatial has done is wire up generative Gaussian splatting algorithms directly into the LLM via this protocol. They have fundamentally changed the user interface for 3D world building.
It entirely removes the need for complex DCC software. A user doesn't need to learn Houdini or Blender. They open a chat interface in their browser and speak to an MCP-enabled agent. The user types, generate a cozy cyberpunk apartment. The agent parses the request, pings the generative splat API, and returns a fully realized 3D GS environment.
And it hooks into everything we just talked about. The user says, change the neon signs to blue and make the floor wetter. The agent accesses the Material Cluster GS global palette we discussed, finds the BRDF prototype for the floor, increases the specular roughness value, and updates the emission values of the neon splats. It executes complex rendering pipeline adjustments purely through natural language.
It democratizes spatial creation at a level we haven't seen before. Anyone capable of writing a prompt can now build, edit, and art-direct complex radiance fields.
Okay. We have gone incredibly deep today. For the Frame development team listening, let's synthesize this roadmap. What are the absolute imperatives you need to be focusing on for the rest of 2026?
The roadmap is brutally clear if you want to maintain dominance in the spatial web. First, WebGL is dead for this medium. Web GPU compute pipelines and streamed level of detail via formats like SOGS are mandatory to handle the memory and bandwidth requirements.
Yep.
Second, you must balance the GPU load by implementing decoupled hierarchical rasterization concepts like Higgs. Third, visual fidelity without physical substance is useless. You must implement sparse voxelization pipelines to generate solid collision meshes for physics and TSDFs for AI navigation.
Right.
Fourth, the baked-in lighting curse must be broken via palette-based BRDF extraction so your users can dynamically relight their environments. And finally, you must lay the networking foundation for 4D streaming, preparing to ingest both time-varying volumetric residuals and live transformer-refined reconstructions.
It is a massive, daunting roadmap. But the computer science is there, the math is proven, the tools are standardizing, which leads me to a final thought I want to leave everyone with, a little bit of extrapolation to chew on.
Let's hear it.
We just established that Spatial's MCP server allows LLM agents to build and edit splat worlds dynamically via text. And we established that Refine can merge and update 200,000 spatial primitives in 15 milliseconds. So if generative AI can instantly modify a world based on language, and the rendering engine can update that geometry in real time, what happens when a frame environment is no longer a static room that you load into?
What happens when the room starts listening?
Exactly. What happens when the spatial environment itself becomes a live 4D radiance field that continuously generates relights and physically adapts its layout in real time based purely on the conversation happening between the avatars inside it? If you are discussing a concept, the room physically morphs to visualize it. The architecture of the space becomes as fluid and dynamic as the dialogue itself.
That is the ultimate convergence of spatial computing and generative AI. The environment's no longer a container, it becomes an active participant.
From a baked-in static point cloud to a fluid conversational reality, that is the frontier. Thank you to the Frame Dev team for joining us on this exploration today. Keep optimizing those compute shaders, keep pushing the boundaries of the web, and we will catch you on the next deep dive.